All right, welcome back to the second video. We're just going to finish this back page here. There's two more cases that we really want to talk about that are kind of special. I'm going to help you guys with the graph. Let's assume that we're graphing this cubic function here using our graphing calculator. And likewise, you could probably graph the quadratic by hand, but we'll just throw in our sketch really quickly. So my cubic is going to come up something like this. Come back through at the origin and come down and come up again. I just use my calculator to make a quick sketch of what we have labeled here as f of x. G of x is a quadratic. It's spread out kind of wide, but interestingly enough, its zeros happen to also be the intersection points with f of x. So it looks something like this. So if I look carefully here, you might be wondering, well, how am I supposed to know which region it is? Well, there are two regions that are bounded by these curves. And therefore, we want to calculate, when we say generally, the area of the region bounded by the curves, we would then include both of them in our solution. There's this one, everything is expressed in terms of x's, so we are in great shape. We could easily work through that if we did top minus bottom, just like I showed you on the front side. Let me throw in a couple more intersection points again, read off of my graphing calculator. The origin's probably pretty obvious to you, and this one is at x equals 2. The problem is that when you go and you try to evaluate top minus bottom, do you see? What is the problem? Do you know? Well, it switches on us, doesn't it? If I think about drawing sort of a representative rectangle for our Riemann sums over on this left-hand region, then the top of my rectangle is controlled by the cubic function, or by my f of x. However, if I look on the right-hand side of my graph and I consider a representative rectangle for that Riemann sum in that second region, then the top of that rectangle is always controlled by the parabola, and the bottom is controlled by f of x. So they switch. When this happens, you have to split up and calculate the area of your the values of your areas separately, and then add them together. So when I go to set this one up, I will write out area equals, and then I would integrate for this first region on the left-hand side. I'm beginning at x equals -2, and I'm rolling until x equals 0. And the top curve was the cubic function, right? Because it waves up and comes down again. If you would like, you can even write just f of x, because f of x is kind of long, call it by its nickname. And we'll write minus g of x. And to be precise, we should include our dx. That would generate the area for this region on the left. And then we would go ahead and add the area for the region on the right. That region stretches from x equals 0 to x equals +2. Right? I would generate and draw my little rectangular Riemann sum pieces starting here and ending here. So that's happening from x equals 0 to x equals 2. And in this case, the top would be the parabola. So I would write g of x minus f of x and dx. And for this one in particular, I don't think I would ask you to do this one by hand because it would just take a lot of time. Let's go ahead and use our calculator. So I'm going to hit math number 9. It brings up my integral symbols. I'll type this in, -2 to 0, f of x, 3x to the third, minus x squared. Oops, made a quick mistake there. Let's fix that. Forgot to scroll down, minus x squared minus 10x. And then I would suggest doing subtract, because you know you're going to subtract it. And then because it has multiple terms, use parentheses. You could also just distribute the negative. It's totally fine. But in case you make a silly mistake, it is probably better to subtract the whole quantity so that you're not making an unforced error. And when I press enter, I should get 12. Likewise, I would do it again. I can press math number 9. I want to make sure I'm going from 0 to 2 this time. I'll type in my g of x first. So we'll do minus x squared plus 2x. And then I'll subtract the quantity 3x to the third minus x squared minus 10x. Sorry for the slow. Maybe you can make me talk faster during that phase, or maybe you're following along and typing in yourself. Can you see it in the glare there? I press enter, and oddly enough, I got 12 again. That doesn't always happen. That's just unique to this particular question. And so the area in total would be 24. Students will often ask me, do I need to write units squared? You do not. There's no units in the question. You're not required to put units in the answer. I would suggest that you don't. If you accidentally write the wrong thing, they will take off points. So you would want to be careful. So anyways, keep an eye out for when the curves switch places on you and what that would mean for your sketch. Last but not least, we want to talk about the other formula that was on the front page. When would you want to use horizontal rectangles? And there are different reasons why you might do that. You could have a function written in terms of y. Notice that all of my equations here are x equals, and then my function is in terms of y. That is typically an excellent indication that you will be representing this one as a horizontal rectangle and using that rightmost minus leftmost curve. Occasionally, you might run into a problem as well that is maybe written in x's, but if you convert it over, it might save you the trouble of breaking into multiple parts or something like that. So make sure you work through the homework because you'll run into some like that. But let's try one together real quick. Find the area of the region bounded by the graphs. If you are forgetting how to graph conic section parabolas, go ahead and just plot some points. Now the downfall here is your calculator will not do x equals, but you can pick y's and plug them in. For example, if y is 0, x is 3. So this should look like that there. I do know that it's a parabola that's opening to the left, so that might help me. Try another point, right? If y were 1 or -1, because I'm going to square, I would be subtracting a 1, so that would be a 2. So 2 should give me a 1, or 2 would give me a -1. And that gives me at least enough information to kind of sketch in, knowing that it's a sideways parabola from my knowledge of pre-calc, it should give me at least a start. And last but not least, x equals y plus 1. Again, you can just plot points. You can convert it over. I did y equals x minus 1. That gave me my y-intercept. My slope of 1 would move me up 1 over 1, and it looks something like this. Here, you would need to work through this on your own in terms of the intersection points. I want to know, hopefully you can see that the area that I'm trying to compute would be this piece right here. That would be the area bounded by those two curves. I do need to know the intersection points for those, however, right here and right here. Now this one we got a little bit lucky because I used that particular point, right, to graph my parabola. So here I could do the same thing and I could try to guess and check, or I could just use substitution, right? 3 minus y squared should be equal to y plus 1. So 0 equals y squared plus y. Let's see, if I subtract 3, that's minus 2. And that would give me, let's see, I would want a plus 2 and a minus 1 for my factors. So the 1, y equals 1, is showing up right here with that intersection point. And when y equals -2, that would give me this intersection point. So let's see, when y is -2, I'll get -1, -2. You could do this problem exactly the same way that we've done the others. I'm going to use a pencil here, and don't write this down. You could try to create those vertical rectangles like we did prior. The problem is that with vertical rectangles, once I get past this line right here, the top is being controlled by the linear function, the bottom by the parabola. When I pass that line, the parabola is actually controlling both. Notice that if I draw a representative rectangle over to the right of that line, I would be between the parabola. And there are ways to do that. But what ends up working out easier, if I can find an eraser here to get rid of that, what works out a little bit better and gives me a chance to show you guys the right minus left curves would be to work with horizontal rectangles. So picture it like this. I could still estimate the area of my curve, but by creating rectangles that move side to side. And the benefit to that here is that no matter where I draw my rectangle, the right end of my rectangle is always lying on the parabola. The left end of my rectangle is always lying on the linear function. And so I can set this up as right minus left from the front side. I would set up the integral of the rightmost curve. That is my parabola, so 3 minus y squared. And I'll subtract the leftmost curve, y plus 1. Everything about this equation, though, is written in terms of y's, and that means that my bounds as well need to be written in terms of y values. So when I go and I look at those intersection points, I want to think about, well, I'm going to start sketching those little rectangular approximations way down here at this coordinate, and the y value at that coordinate is the -2. So notice I'm using the y values on my bounds. I would build up and up and up all those infinite rectangles, and I wouldn't stop until I got to 2, 1 when the intersection point occurred. That happens when y is 1. And again, notice that these are y values, my function's written in terms of y's, and I have a dy on the end. You have to be consistent. You cannot mix your variables. When you go to type it into your calculator does not care what letter you are using. So do not try to torture yourself. Just go into math number 9 and use the values that are here. So I'm going to use 3 minus x squared because it's just a variable name. And then I'll subtract my variable plus 1. And I have to make it match on my calculator. And that is where I would get 4.5. So it's really, really important that you practice this. I would suggest that you start with our textbook. All the solutions are posted online so you can follow along. If you finish that, check out the Delta Math and they'll give you some additional practice. Thanks for watching. Best of luck.